Okay. Hello everyone. Today's class, I think I just give you this slide information. Just to summarize what we did before. And then we are going to introduce you to the new techniques we call the variation of parameters. Okay, now, so far what we have done is we are having differential equations and we are able to make it on the second order, right? The second order, the differential equation with the second order, which means we have the second derivative. If we increase the order, like maybe the third or fourth, we are still able to use the same techniques, the undetermined coefficients. So for example, if I take the third order and then equaling to e with power of x cosine x, the process is still the same. Okay, the process is still the same. So first, we process the homogeneous, take the auxiliary equations, and then we find that this can be written as m cubed plus m squared equal to 0. Okay. And then we know that this is going to be m plus m squared plus 1. So m1 equal to m2 equal to 0 and m3 is equal to negative 1. Okay. And we can write down our complementary solution, YC. So C1, because it's e with power of 0, right? So it's 1. And then plus, because it has the same root, we need to multiply with x, so C2x. And then plus C3, and then e with power of negative x. So this C1 and C2 is supposed to be the same constant, but because they are the same, then one of them needs to be multiplied with x, because they have the same root, 0. If it's one, maybe it's e to the x, and then the other one is x e to the x. Okay, so we need to multiply with x because of we need to make it linear independent. Okay. So that's the YC. And then we propose that because we have e to the x cosine x, then yp, okay, remember we have cosine, it means that we will have something multiplied with cosine plus something multiplied with sine, or a constant. And then we have e with power of x, so we multiply it, e to the x, to both cosine and sine. So we are going to have, let's say, coefficient a, e to the x cosine x, plus b, e to the x sine x. Okay. So let's try with this one. And I think it's still okay, because we are not really messing up with the ones. So let's try to check and find out the constant. But I think I will leave this to you. But what we have here, what we need to check the first derivative, the second derivative, the third derivative, and I know this will be takes time and really, really long. But hopefully, we can adjust all these terms, and I think we only need the third order and then second order to be put into our equation. And try to put that and find A and B. Okay? And after we get all of those A and B, then we are going to be able to find our y, which is our yc plus yp. Okay? So basically all the differential equations, most of the problem actually can be solved through this undetermined coefficient, as long as they are able to be confirmed their linear independency. And actually you can guess from the right side of the equation. You can see that it has a polynomial, exponent, or trigonometric, or combination of all of them. Then perhaps we can take to this method. Okay? And this is actually quite useful, this method. Okay, I think that's it. I think the rest we can have some practice, especially for proposing the YP. I think that's I think the core problem in this method. Okay. So the next method, we call it the variation of parameters. Variation of parameters is a method that will complete the weakness in undetermined coefficient. Okay, for example, let me show you one way. So let me write variation of parameters. Let's consider first, consider the y double prime plus y equal tangent x. Okay. Now we have a tangent, something that is missing in previous method. The previous method can be solved easily through sine, cosine, because they are complementary each other. When we derive, they will still be able to see. We can still observe sine and cosine every time we derive. But tangent, if we derive tangent, for example, if we derive, let's say we have a function of tangent. If you want to derive, we are going to have the secant squared, right? We derive again. We still have those sequence like that, and then having this tangent, because we have a secant tangent for the secant. And if we maybe try more, well, we will have some product rule, something, right? Okay. So how do we make it into our solution? solution because I don't think the underlying coefficient will help within this problem. Okay? So to find yp, to find yc is still the same, homogeneous, okay, but yp is the problem. So to find yp, we are going to introduce this yp in terms of the help from other function. Let's say u1 y1 plus u2 y2. So u is another function, or maybe u is a function. Okay, and or maybe let me write u is maybe here, and let's try to take first derivative. So u1 prime y1 plus u1 y1 prime, and then same thing with the second one, u2 prime y2 plus u2 y2 prime. Yeah, I think it's a little bit confusing, my writing. Let me make it u like this. Okay, and then combine this with this u2 prime and y1 prime with y2 prime. Okay. Let's combine those two. So u1 prime y1 plus 2 prime y2 . Okay. Okay, and the important thing here, this yp, it need to satisfy if I write ly equal to tangent x. Do you still remember L? L is the linear operator in the first order. Related to the linear equation, the linear operator. So we have B, we have L, there's just some symbols in the different. Just to help you to remind that L is the linear operator. Okay. And it requires that this u1 prime y1 plus u2 prime y2, it need to be equal to 0. And then yp prime then is equal to u1 y1 prime plus u2 y2 prime. Okay, and then we take the second derivative. Okay, so u1 prime y1 prime plus u1 y1 double prime. Well, let me write that bracket first, and then plus u2 prime y2 prime plus u2 y2 double prime, and then we combine the u1 prime y1 prime plus u2 prime y2 prime. So combine this two and combine u1 y1 double prime plus u2 y2 double prime. Okay, and also what we need to look at here is y1 and y2 are solutions of y double prime plus y equals 0, right? So we could say that the y1 double prime need to be equal to y negative y1, and y2 double prime need to be equal to negative y2. Okay. Now, okay. Now perhaps we will have some confusion here, but let me give you some analogy. Okay. If we have y double prime plus px y prime plus qx y equals 0, from this equations we could have or y1 double prime is negative px y prime minus qx y. This is just to slide over there and just look at different perspective. So this yp double prime let me just copy this. Okay. And let this u1 y1 plus u2 y2 is equal to y. Okay. So we take this approach and make it here. We take that and we are going to have this, or let's say this is become or maybe just write this first, and it's become this yp double prime we can write this and make it is equal negative y, because the y1 double prime becomes negative, and it will be negative y. Okay. Now we could write this and see the form at the end that this y p double prime, when we plus with this, is actually coming to the original one. So we have y double prime plus y equal this u1 prime y1 prime plus u2 prime y2 prime. Okay. So we have now here. Okay. So the key is this one, okay, this u. So first, this u and this requirement here, okay. So as conclusion here, need to solve two equations on u1 and u2. So first is u1 prime y1 plus u2 prime y2 equals 0. And the second is u1 prime y1 prime plus u2 prime y2 prime equal a function of x. Okay, let's say a function of x. Okay. Because this is, we are going to have, see, our question is tangent. So we are getting this equaling to our function. So by writing this, our approach to solve this kind of equation, we have a it's like a linear equation, right? So a linear equation like when you did the finding with the two variables x, y, right? So we can make a matrix from here. We can make a matrix. So it's a little complicated at the beginning to prove it, but in practice, it's actually solvable. And the one that has or you need to use this method is really limited. So not all problems can be solved through this way. I think all the problems can be solved, but it really takes time. But for a problem like the tangent or the secant, we can solve through this variation of parameters easily. Let me show you how. We haven't yet go to the tangent. We only have what we need to solve is this two equations. We need to find u1 and u2. So from here, we are going to build a matrix. Defined through matrix. Okay. But before we define through matrix, we can try our best to solve this. Let me go through a new page. Maybe we'll copy this first. Copy here, paste. Okay. First, we can write down that the y double prime plus y equal tangent x. We can build up the auxiliary equation first. So we will have plus minus I. So we could have the alpha is 0, beta is 1. So we could write this yc. If you remember, this is c1 sine x. It's a constant coefficient, cosine x, like that. And suppose that we can try y1 as let's say cosine x, and y2 is sine. And we tried this too, and we make out through our equations. So this will be negative sine x. Y2 prime is cosine x. So u1 and u2 will be the variable. Okay. So we try to check through our equations. Let me write again. U1 prime y1 and plus u2 prime y2 equals 0. So we will have u1 prime y1 is cosine x plus u2 prime is sine x equals 0. And then this will be the y1 prime is negative u1 prime sine, right? And then plus u2 prime cosine x equal tangent x. This is the second one here. I think we can move here. Let me copy this to make it clear for you. Okay. So this is 1, this is 2, this is 1, this is 2. And to solve this, like usual elimination or substitutions, we can, let's multiply with sine x and cosine x for the bottom one. So we will have u1 prime sine x cos x plus u2 prime sine squared x equals 0. The bottom one, negative u1 prime sine x cosine x plus u2 prime cosine squared x, and then this will be sine x, right? And we can plus this. So this will be cancelled. So we are going to have u2 prime sine squared x plus cosine squared x. This will equal to sine x. So u2 prime is supposed to be sine x. And u1 prime, we can substitute. It will be negative sine squared x over cosine x, or this will be what? Negative tangent x sine x, right? Okay, now this is the derivative forms. What we need to look for is the u2. u2 is negative cosine x. Okay. And u1 is, we need to do some derivative integrations, but I already write the answer for you, so you don't need to worry about that. But you need to check, because I did it through calculators. So not calculators, just software. So take this sine x minus 1 sine x plus 1. So yp is all these combinations. So yp is u1 so this is I would like to say more how to say that rough approach, really rough. Okay, I will show you later more soft approach that I think will be applicable for us. We can see that the end at the end, this is our yp. So general solutions yc plus yp is c1 cos x plus c2 sine x plus half cos x ln Okay, so what we did here is basically the first idea. Where's my? So let me just take some notes here. Okay, so notes that this idea is came first that we take approach yp as a having a functions, another function u. And this y1 and y2 is actually y1 and y2 are form of the solutions from homogeneous. Okay? Form of fundamental set of solutions. Or we say that this is the homogeneous form. I think it's easier to follow. Okay. So first we propose to solve the solution. We take y1 and y2 from our homogeneous form, from the fundamental set of solutions, and then we can solve through our linear method, elimination, substitution. But it seems still rough. Okay, we need to have more general approach to find our yp, which includes the matrix, and to solve the matrix, I have to still remember the Wronskian. We need the Wronskian to solve. The Wronskian is determinant, right? The determinant using the matrix. So we are going to solve the problems here using a little bit of matrix. Okay. But I believe the problem for this variation of parameters is, I think, for only the second order. I think if it's third order, it will be 3 by 3 matrix. So still possible, but I don't think it will be human in this sense. So I think maybe just the second order. Okay, let me give you an idea how to solve it using Wronskian. So what we demand is, let me write this one, copy again completely. I think if you skip the first part, maybe not really pay attention, I think it's okay. Just pay attention to this one, okay? This is the core of the techniques. So we are going to take this into matrix, okay? We are going to build our Wronskian. Usually our Wronskian is like this, okay? And we are using this Wronskian to state whether our y1 and y2 is they are linearly independent, right? But now we are going to set this Wronskian and changing one part with this solution. We call this Cramer's rule in the matrix. Well, I'm not sure, like in the next part of the chapters, we are going to find a matrix, but we will use that matrix here. So yeah, it's a little bit awkward. So yeah. So I hope this method is the matrix. You're still familiar with it. So the Wronskian, the determinant. Okay. So we say the W1. So it's called the Cramer's rule. So 0 f of x, y2 prime. So just changing the first column. And you have W2, you can change the second column. And this will be 0 and f of x. Okay. So Cramer's rule state that u1 prime is this, and u2 prime is, where the Wronskian is the determinant. So you are finding the determinant, and you put here, you could easily nicely done u1 prime. And it can be used in most variation of parameters problem. So you can have priority in your solution. Since this method, it actually can be used for many cases also. But some cases maybe takes time. Maybe it's better if it can be solved through the undetermined coefficient. I think still okay. But sometimes the undetermined coefficient also depends on the way you solve the algebra. Like if it has like many coefficients, right? Maybe if we take to these variation of parameters, maybe it can be simple. But of course, since we need the Wronskian, like we have y1, y2, and y1 prime, y2 prime, so we need to make sure that we are going to be able to find this derivative, and when we solve this determinant, we can make sure that, okay, we have our answer. if maybe the derivative is a little bit complex, and when you do this u1 prime and u2 prime, maybe it's still a big fraction, and you need to do integral to find u1 and u2. So there will be some layer of difficulties. So yeah, I believe I gave you some glimpse on how this method should be. Yeah, W is the Wronskian if you would like to take notes. Okay, we have I think learned about that before. So we still need to find the u1, which is the integral of that u1 prime and u2, right? And y1 and y2 propose from homogeneous form. Okay. Let me give you a quick example, just to show you the process. Maybe not completely work on how to find a solution, but just give you an idea. Okay. Okay, I hope I can move a little bit to the next page. Okay. So let me go through y double prime minus 4y prime plus 4y equal x plus 1 e to the 2x. Okay. Now in undetermined coefficient, we can solve this, I think, not really difficult. We know this one, so I believe we need just to multiply with this and then take some coefficient and solve this solution and match all the coefficients, and you can find your coefficients, right? And you can find your y. But in variation of parameters, we can also doing this. So variation of parameters depends on this also. So first, this is f of x, okay? And first, take the auxiliary equations. You will get your y1 and y2. Okay. So the y1 and y2, if you look at the auxiliary equation, perhaps it will require some e, right? Some e something. And then writing the Wronskian, and then put into the determinant matrix like that. Find the Wronskian, and then find another one for y1 and y2. Okay, I think we can. I think. Let me just solve the auxiliary one here. So this will be m minus 2 squared. So m1 is equal m2 equal 2. So we are going to have yc is c1e with power of 2x and plus c2 x e power of 2x. So this will be our y1 and this will be our y2. Now we put all y1 and y2 all together here, and this will be the derivative, and this also the derivative. Okay. And take the determinant, find the determinant here, cross multiply, minus, subtract. So 2x e 4x plus e 4x minus 2x e 4x. So we get e with power of 4x. So I think it's quite nice. And the same thing with y1 and y2. We take y1 0 x plus 1 e with power of 2x, and then x e to x, 2x e to x plus e power 2x. And then do the same thing with this. So this will be e 2x, and then 2e 2x, this will be 0, and x plus 1, e power 2x. And then cross multiply, and because one of them is 0, so I think our solution, or our Wronskian, is not too difficult to write. This is x e for x, okay. And y w2 is x plus 1 e for x. Now u1 prime is Wronskian 1 divided by the general Wronskian. So minus, I think it's nicely done. We can cancel this all together for the e power 4x, right? Also the other part, we can cancel this easily. Right? So we can find the u1. So u1 prime, let me write, negative x plus 1, or negative x plus 1, and u2 prime is x plus 1. So we can integrate. This will be, this is negative x squared minus x, right? So we have 1 over 3 x cubed minus half x squared. u2 is half x squared and plus x. So yp, we can arrange all this together. So negative 1 over 3 x cubed minus this, and y1 is e to the 2x, and a plus I think you can solve and simplify, but I think enough for yp. Okay, if you want to find yp. If you want to find general solutions, then you need to add yc plus yp. Okay. Okay, I think we are going to stop here. So yeah, we'll just stop here. No feedback time. Feedback maybe next week. And the midterm will be in 2 weeks. The Tuesday.